draft physics video. Okay, it's going to be delicate. I don't mean any offense by this video, or whatever ones I make in this series. It's just when I'm watching physics lectures, sometimes I see something where I think they made a mistake. Not only a mistake from my theory's perspective, but a mistake almost from their own theory's perspective, in the sense that their theory is close, but it's not quite right, and so it gets a little bit, you have to be careful in how you state what's happening, because they don't quite see it consistently, let's say. In certain circumstances, the energy does a certain thing, and in another circumstance, they'll allow it to do something subtly different. That kind of thing. So anyway, I just think this mistake is a mistake by his own. I think you could understand the mistake. And so I just figured I should point it out. Because frankly, it's an MIT professor, and you should point out when you see them make a mistake. Yeah, it seems the right thing to do. So anyway, and this is a really important subject to me in terms of the understanding magnetism and what's really happening with a magnet. So I probably should pull up the DraftScience website to use that illustration, and then I won't have to draw another picture of a magnet, just for the field effect idea. Alright, so let's start, and then we'll see what we need to illustrate with either graphics or whatever, drawings, such.
Suppose I have here a magnet, North Pole, South Pole, and the magnetic field, magnetic dipole field, is sort of like this.
Alright, now that's like a superficial description of what the magnet's actually doing, so it's by my definition, not theirs. What's really happening is this is filtering the gravitons, and it's just a filter. It doesn't create any energy, it doesn't move anything, it doesn't do anything except filter, in the sense that stuff comes in one color and it leaves another color technically. So all the stuff that's, say, red or southish comes into the magnet and it comes out this end northish, and anything northish that comes in this way ends up leaving southish, red or blue, however you want to describe it. And so there's more of it getting filtered purer here and here. So this is pure red, this is pure blue, and then as you go on the sides, it starts to change in strength. Red gets mixed with blue, and right in the middle would be the weakest point, where you have a mixture of red and blue. Proceeding.
And now I bring in the vicinity here a piece of ferromagnetic material. It would be a wrench.
So he's going to do a demonstration with a wrench. So understand, so ferromagnetic means this is the kind of stuff like a piece of steel, iron, and it's capable of becoming magnetic when it's in the presence of a magnet. That's why it sticks. That's why a magnet sticks to something made of iron, is because the iron changes into a magnet as the magnetism affects it. The little domains inside flip to be appropriately aligned to be the opposite of the other magnet, whatever the strength of the field is. If it's feeling more blue, it turns red. If it's feeling more red, it turns blue.
What happens now is that this ferromagnetic material will see this vacuum field. This is called a vacuum field, it's an external field. Right. And so these domains in there...
Right, so it won't see it, obviously. It will penetrate the material, the tons, the red tons, and in that process, it will move the domains.
Trying to line a little bit, degree of success depends on how strong the field is, depends on the temperature, depends on the kappa m of that material. But certainly...
So the kappa m would just mean how capable the material is of having its atoms all arrange.
This will become sort of the South Pole, this will become the North Pole. That's the...
Right. So that's all. He should have left it there, and then everything would have been okay. It's now we're getting to the part where it's into. So this is a permanent magnet. This magnet can't change its magnetism. It's fixed permanently. This is a magnet that can be changed. If I brought another magnet in this way, this thing will start changing. So this is a changeable magnet. This is an unchangeable magnet.
That these dipoles are going to align themselves. They're going to create themselves a field in this direction. They're going to support that field.
Okay, now there's not going to be any other field created here. There's no supporting field. This one is just a filter. This one's a filter. And as this one becomes a stronger and stronger filter, as you bring it closer, it becomes more and more of a magnet. It will produce rays, red and blue, in a stronger and stronger proportion. But there's nothing happens where there's any support between them. This force here and this force here don't interact at all. All you can do is make this magnet stronger as you bring them closer, and because it'll be the south and the north, they'll be attracted by the rules I've explained.
And so the net result is that the field inside here becomes very strong. And so what
so it doesn't become any stronger than the relationship it is to the other magnet. So the closer it gets to the other magnet, the stronger it becomes, and it becomes more likely that they're going to stick together. And once they're stuck together, the field becomes as strong as the magnet's capable of producing in terms of another filter.
What happens with these field lines? They go like this. They're being sucked into this ferromagnetic material.
So I would say that rhetoric is just completely nonsensical. Nothing gets sucked in. There's no bending of the field in any way. The two magnets are straight line producers. The light coming off this magnet, so to speak, the rays of red and the rays of blue are not affected in any way. The only thing that happens is these materials, because one is blue sensitive and one is red sensitive, will end up getting pushed together because they're leaking the opposite potential. So nothing's being trapped between them. There's no electron on electron force between them. It's a proton on electron circumstance, and because of that there's a low pressure between them. But there's no bending of the fields at all. No energy or none of the magnetic force is at all bent.
It's very hard to know exactly how they go, and the field here will weaken.
Okay, the field here will not weaken in any other sense than you've now introduced a south pole here. So you have a north pole here, and so if you were to bring an electron or a proton in here, using those as the constituents of a magnet, that's what they really are. The electron and the proton are actually the monopoles of magnetism. So what's really happening is now you have a south pole close to this object. So whatever object would be here that would be sensitive to magnetism, if it's attracted to this north end, it's going to be repelled by this south end. And if it's attracted to the south end, it's going to be repelled by the north end. So it's going to be affected only because there's two fields now, and one of the fields is pushing it out of its ability to be attracted.
And I'm going to demonstrate that to you. That is actually very easy to demonstrate. The way I'm going to demonstrate that is as follows. I have there a setup whereby we have a magnet and we have a nail and we have a string. And
so understand the nail is just another piece of steel that's going to create another magnet. So it's like so here's where the nail is going to be. So it's like having a a magnet here, and it's going to do the same thing this piece of steel did. It's going to create a south end and a north end. So now it's going to be attracted to this north end, but it's going to be repelled by this south end. So that's going to be a problem. It's going to have two forces affecting it. And because of those two forces, it's not going to be able to be as attracted to the northern end, because it's going to be, some of its domains are going to be switching to ends. Its magnetism is going to diminish because this S means this wants to go north. So it's getting two influences that are switching its domains, and they're switching it in two opposite directions. So the nail becomes less and less of a magnet because some of the magnets are going north to south this way, some of the magnets are going north to south this way. So you can understand if the magnets are inverted, they're not going to be capable of producing the same strength.
The nail wants to go to the magnet. The nail itself is ferromagnetic. So the nail loves to go this direction, but it can't. So it just sits there, it hangs there in space. First of all, what I want to show you is that if I bring paramagnetic material in the vicinity, that magnetic field configuration here is not going to change at all. Paramagnetic material has a kappa of m so close to 1 that nothing is going to happen. But the moment that I bring...
There's no domains, not enough domains to switch.
Ferromagnetic material, for instance here, then you get a field configuration change, and if I do that...
So in saying a field configuration change, you should point out that the configuration changes is that the location where the magnet is now the ferromagnetic nail is now not being influenced by just a north end, it's being influenced by a south end, and so all of its domains, half of its domains maybe, are switching, depending on how strong the ferromagnetic wrench, how close it is to the magnet, and how strong its magnetism is going to be. The stronger its magnetism gets, the more the nail starts switching the wrong way to be attracted to the magnet.
If the right way, then the nail will fall. In other words, there is not enough magnetic field here in order to hold the nail in that direction.
So it's not that there's not enough magnetic field, it's that there's two conflicting magnetic fields, and the conflicting, the opposite magnetic fields mean that the nail is not going to know which, its domains are not going to be consistent anymore. They're going to be opposing each other. And by opposing each other, the nail is going to become a weaker and weaker magnet.
And I'm going to show that to you there. Need some power here, I believe. And we have to make it dark here.
Sorry, a little bit of prep
shadow
work.
projected for you.
Let's speed it up a little.
And the shadow projection, you will see coming very shortly. There's a carbon arc. Have to give a little bit of time to start. There's the carbon arc. But now you see the nail. And you see the magnets. You see that? It's exactly the way I drew the picture. And
okay, so there's the nail, and here's the magnet. So let's just say that's the north end. That means this has gone south, and this has gone north, the end of the nail. And it's one kind of magnetism. That's all. The only magnet creating magnetism in this is this magnet. So this is all south and this is all north. There's no conflict. When he brings the wrench in, that's going to create a different magnetism that's going to start switching the domains in the nail, and the nail will fall.
here, I have here a piece of aluminum, which is paramagnetic. I can bring that through the field here. Nothing happens. My hands, believe it or not, are definitely not ferromagnetic. So I can also bring my hands here. Nothing.
Yeah, so nobody's impressed by that, right? Right. So obviously paramagnetic creates a very weak magnetic change, very weak.
So magnetic fields not disturbed in any way, in any serious way, either.
The trick was there also, by putting it in between the nail and the magnet, you would defeat the purpose, because that would just create I could probably do it better on one of the other images, but to say this is the north end, if you put a piece of metal in here, it would just create a south and then another north. So you'd still have a consistency of all north facing the nail. So you wouldn't affect the magnetism of the nail by putting something in between. Even if you put a piece of steel in between, the piece of steel won't even affect it, because it'll create the same magnetic orientation as the magnet. So you'll just create another north-facing magnet. So you won't affect the nail, because you're creating another magnet and it's even closer to the nail. So you might make the nail attract even more. So that was kind of it wasn't a very effective way to demonstrate there's no field change, because actually when he put the aluminum in there, that's what actually happened. The aluminum went north and south, exactly opposite this. I mean, exactly the same in the sense that the north end became the bottom and the south end was the top of the piece of aluminum. So even if it did create a very strong magnetic field, you couldn't demonstrate it that way. And of course it won't block the magnetism, because it's paramagnetic, so it will create a little bit of a magnetic field. So that was kind of wrongly stated, I would say.
By paramagnetic material, aluminum, or my hands, which I think are also paramagnetic, but I'm not sure. I'm not sure.
Yeah, well, the point is you can't demonstrate how it would block a field by saying it's partially magnetic. If it's anything partially magnetic, well, this is north, this surface will go south, this bottom surface will go north, so again the nail will still be facing a north magnet. So it's not very, if your hand was made out of iron, this would still just be the same truth. You would stick your iron hand in there, and that doesn't demonstrate anything, because of course your iron hand isn't going to block magnetism.
Whether I'm diamagnetic or paramagnetic, but it doesn't make any difference, because in both cases there is no significant change of the magnetic field.
Well, there's no significant change, because even if there was a significant change, in the sense that you put ferromagnetic material in there, you would have had the same exact effect. Nothing would have changed.
Now I have a wrench here. Here, there's a wrench. You see it? Okay. And now I bring the wrench close to that magnet. My major worry is that magnetic field is so strong that once the wrench goes, there's no way I can get it off again. So I get only one shot at it. And there goes the nail.
Okay, so what happened there is exactly what I'm saying happened there. Okay, so as he's bringing the wrench in, the wrench is going south. So here you have a north influence and a south influence. And those two influences are on this nail. So the nail was all south and all north. So it was attracted to this magnet because everything in the nail was south here and north here. And now this south pole is changing the domains in the nail. So now the nails, some of them are switching over to go north to meet this south pole now. And so by that happening, the nail's losing its magnetic consistency. It's like they're tugging against each other. And if you do that to a magnet, it loses its magnetism. If you force magnets to go their wrong polarity, you'll eventually you'll neutralize the effect of their magnetism.
And there goes the nail. So what you saw now in front of your own eyes is that I changed the magnetic field configuration.
See, now saying I changed the magnetic field configuration is probably accurate, but you have to, what he said and what he illustrated doesn't explain how the change in the field configuration was you introduced the opposite polarity, and that opposite polarity diluted the magnetic strength of the nail to the north side of the magnet.
Such a way that the field was not strong enough to pull in the
so he's saying this field wasn't strong enough to pull in the nail, when that's not what happened. What happened was the nail's magnetism weakened, and that's why the nail fell, is because it became less of a coherent magnet.
Now comes
okay, so that's it. So anyway, yeah, so it's sort of important. So again, this is just to point out, my argument is there's polarized gravitons actually, but the polarized field energy comes into a magnet in both colors, and the effect of a magnet is whatever side you're on, whatever the outside barrier is, that's what it comes out as. Now the mechanism inside is a little more complicated than that, but the filter is that simple. So stuff coming in this way red, if it's going on a straight vector right through this black, it comes out black. Something comes in this way red, yes, it goes black and then it ends up turning red. It just always comes out whatever the outside of the magnet is. But it's all straight line force. They never twist or turn. The force is always straight lines. They don't blend. They don't fuse. They don't merge. They only affect something directly. The fields can't be. They can't. The field energy force can't affect force. They can't. Superposition. Nothing can. They don't mean anything. Nothing happens until you put something in the field and make it create a filter. Unless there's something that can filter, something that's an electron or a proton, something that has electrons and protons in it, in an arrangement that is not making the electrons and protons neutralize because they're all in different positions. But that's the only thing the energy can affect, is something affected by blue or affected by red. Protons and electrons, really. So anyway, enough of a video. Until the next time and such.